Thank you for the introduction. Good morning to everybody.
Good morning.
Just a moment. I will share my presentation. Can you see it?
Yes, it is visible.
Okay, thank you very much. So, good morning to everybody. I would like to thank you, thank the organization, in particular Dr. Menal Gupta, for having invited me to this workshop. So, my talk is on green chitosan. Sorry, one moment, please. Okay. So my talk is on green chitosan-based membranes as proton conductor for fuel cells. Before to begin my talk, I would like to show you where is my university. University of Salento is in the south of Italy, a beautiful place rich of history and also a wonderful sea. There in my laboratory, which is the Applied Physical Chemistry Laboratory at the Department of Engineering of Innovation, we have conducted research in many areas. Zinc air method to recover spent zincate solution from tapered and flow batteries by using batteries and aluminum trashes. Novel non-platinum electrocatalysts for oxygen reduction reaction, and nanomaterials by using template electrodeposition of many kind of structures, nanowires, nanotubes, nanoparticles, and so on. Also, we studied porous anodic aluminum, so the best conditions to anodize aluminum in order to obtain tailored characteristics of the anodic aluminum membranes for specific applications. And finally, the use of novel materials for fuel cell membranes, in particular chitosan. So today I would like to bring to your attention our last results on green chitosan-based membranes as proton conductor for fuel cell. And before showing our experimental results concerning this kind of materials, I would like to introduce you to the topic in order to understand better why we are trying to use green materials. So I will make you a short introduction on green materials and biopolymers and a brief basic information on how a fuel cell works. Then we will analyze commercial and most used polymer membranes for fuel cells, arriving to chitosan and its features and promises. Finally, I will discuss some of our results obtained by our research group in the last years by proposing a novel method to produce chitosan-based proton-conducting membranes, the ionotropic gelation method. So what does it mean green? We often listen to green materials as materials that are local and renewable. More in general, the term green or sustainable often refer to products, services, or practice that allow the economic development capable to ensure the satisfaction of the needs of the present generation without compromising the possibility of future generation to realize their own. So we can describe a green product as a product with less environmental impact or less detrimental to human health than the traditional equivalent product. So we think to green materials as energy efficient material, durable, and often they they have a low maintenance requirements, free of ozone-depleting chemicals and toxic compounds, often made of recycled materials or of renewable and sustainable materials sources. For example, plant materials that grow quickly are for the most part renewable. They are obtained from local resources, and also they are biodegradable or easily reused. Water polymers, everybody knows that the most simple definition of polymers is these polymers are chemical compounds with a high molecular weights constituted by repeated chemical units. We have synthetic polymers and natural polymers. Synthetic polymers are made by men in a laboratory or in industries, and starting from petroleum derivatives. Natural polymers, instead, can be obtained by extraction from raw natural materials. The main source of raw materials are animals, plants, and in general living things. Also microorganisms, for example, some examples, starch, cellulose, chitin, alginate, protein, and so on. Why scientific research interest in natural polymers? For two main reasons: ecological reasons and economic reasons. Most synthetic polymers are not biodegradable, and this causes serious environmental pollution. A strong example comes from the northern part of the Pacific Ocean. In recent years, an island of plastic with an area of extension equal to twice the Texas for 10 meters of depth has formed, as you can see in the photo. This island is created by 4 million tons of waste at the sea that thicken in that area for a particular combination of currents. This is only a representative example. We have many other problems. For example, the microplastics fragments of less than 5 millimeters that through the fish arrive on in our dishes. Economic reason, because fossil fuels are destined to run out, and so we need renewable raw material source. This is important not only for polymer synthesis, but also for energy source. So where we would like ideally to go to solve these problems? We would like to arrive to a circular economy, which is an economic system aimed at eliminating waste and to have a continual use of resources. So at this aim, the scientific research of the last years has been focused on the development of green chemistry strategies. In the field of polymers, the main task is to transform natural sources or agricultural products waste into biodegradable products with high added value to be used as raw materials. So now let's see simply what is a fuel cell. A fuel cell is an electrochemical device able to transform the chemical energy of a fuel and an oxidant directly into heat and electricity. It is similar to a battery, but it can continuously, at variance with respect to the battery, it can continuously produce electricity as long as fuel and oxidant are available. Oxidant is typically oxygen or air. If the fuel is hydrogen, the device delivers electrical energy and heat without the production of pollutant emissions. And this is really important, because considering the zero emission released by fuel cells and the high range of application that they can cover, these devices are considered as the preferred energy conversion devices in the 21st century. Fuel cells are divided into several types depending on the operative conditions and consequently the electrolyte used. The research I present today is focused on novel biopolymeric membranes for fuel cell. So let's consider now some aspects of a polymer electrolyte fuel cell. This type of fuel cell works with a polymeric electrolyte that, depending on its chemical composition, proton conductivity, mechanical and thermal resistance, and rheological properties, can operate in different temperature range, typically going from 60 to 120 degrees centigrade. In our group, we have studied the possibility to use this fuel cell at room temperature. In general, so what are the advantages of this type of fuel cell? The low operating temperature, the easy and fast startup, thanks to the low temperature, high power density, no corrosion problems due to the use of polymeric membranes and also to the low temperature, and an easy fabrication. The disadvantages are located in the cost, because the commercial electrocatalysts and membranes are really expensive, and because the commercial catalyst is platinum. Platinum has a poor carbon monoxide tolerance, and also the need to have a water management inside the cell, because we need water to have high proton conductivity. So here you can see a basic scheme of a polymer electrolyte fuel cell, and in the next slide you see an exploded view of a polymer electrolyte single cell. We have two ending plates together with anodic and cathodic flow fields, hosting a series of channels to deliver both hydrogen and oxygen. We have in the middle the membrane electrode assembly here, which is the key component of the fuel cell. The membrane electrode assembly is constituted by a proton conducting membrane, so our polymer, sandwiched between two gas diffusion layers, the electrodes, which host the catalytic layers. In the membrane electrode assembly, the electrochemical reaction takes place with the delivery of the electricity and the release of heat. When the fuel is hydrogen, the electrochemical half reaction are the reduction of oxygen and the oxidation of hydrogen. In the next slide, so you can see a photo, an exploded photo of the polymer electrolyte fuel cell. And let's say something about the membrane, which is the topic of this talk. What are the role of a membrane in a polymer electrolyte fuel cell? The roles of the membranes are conducting protons from the anode to the cathode, insulating electrons to force them moving in the external circuit, separating hydrogen from oxygen, and physically supporting the anodic cathodic catalysts on both sides. The most common membranes are based on perfluorosulfonic acid ionomers. This type of membranes are commercialized and usually reported in literature as a benchmark material. The most famous and also the first developed polymer for fuel cell was commercialized by DuPont with the trade name of Nafion. Nafion has almost all the necessary properties to be a good fuel cell membrane. It's composed of a perfluorinated backbone with side chains that are terminated by strong acid sulfonic groups. So the resulting membrane has a semi-crystalline structure resembling Nafion, which allows mechanical stability, and high ionic conductivity provided by the strongly hydrophobic terminal side chains and the sulfonic functional groups. The most performing working conditions of Nafion require wet conditions and the temperature lower than 90 degrees centigrade. Also, Nafion suffer also from various problems: water loss, viscous elastic relaxation at high temperature, high alcohol permeability. This is a big drawback, especially for direct alcohol fuel cells, and moreover, they are still too expensive. Also, they are not green materials. So why chitosan? Among various biopolymer complement to ionic cross-linking, which is necessary to give proton conductivity, chitosan represents one of the most promising for its suitable properties. It's a low-cost, eco-friendly, biocompatible, and has a low permeability to alcohol. It is a renewable material and is soluble in water under slightly acidic condition, thanks to the presence of amine groups. It has good film-forming properties, and this is really important to fabricate a membrane, and contains 3 different polar functional groups. These groups gives to chitosan the capacity to attract water and the ability to be functionalized. As told before, chitosan is a renewable material, and it is derived from the alkaline deacetylation of chitin, one of the most abundant natural polysaccharides on Earth, and usually found in crustacean shells, insect, molluscan, and fungal mycelia. Nowadays, the principal source of chitin is shellfish waste. Chitin has a structure similar to cellulose, as you can see here, with hydroxyl group replaced by acetamide groups. Chitosan is the N-deacetylated derivative of chitosan, obtained by treatment with 50% sodium hydroxide. As you can see here, chitosan has polar functional groups in the structure, specifically hydroxyl, here, primary amine, and either C or C groups that facilitates the chemical modification of chitosan. Also, chitosan chains are bonded through intra and intermolecular hydrogen bonding, responsible of the good film-forming properties. Another important information is that chitosan is a copolymer, so pure chitosan does not exist in nature. Chitin and chitosan so tend to form a copolymer, and in nature chitin is commonly at 70–90%. So we have we say that we have chitosan when the N-glucosamine units are higher than 50%. So chitosan, as said before, is soluble in slightly acidic solution, so is a cationic polyelectrolyte, thanks to the protonation of the amine groups and breaking of hydrogen bonds. Thanks to this chemistry, chitosan solutions are often used as a precursor to synthesize polymer membranes. So the promise of chitosan as biopolymer electrolyte for fuel cell here is read as by the increase in research interest along the year. Notwithstanding chitosan and derived material were discovered 200 of years ago, scientific research on their possible application started in 1983, when the acetylation method to extract chitosan from chitin was proposed. So after that, the number of publications significantly increased only after 70 years to the discovery of chitosan. In this figure, we can see that the increase of number of publications collected on Web of Science database for the topic chitosan and fuel cells. In the last, you can see that in the last 15 years, the research studies on chitosan membranes for fuel cell has been gradually grown, and it is still under development. All the study, by analyzing the paper, we see that all the studies are focused on the fabrication of proton-conducting chitosan membranes by following two steps. A first step where the pure chitosan membrane is fabricated, and the second step where the chitosan membrane is functionalized to increase the proton conductivity. Also, we noted that not so many paper reports on fuel cell characterization of these membranes. Most of them report only proton conductivity data. So, as said before, chitosan undergoes a chemical equilibrium in slight acidic solution and becomes insoluble at high pH. So, the capability of chitosan to turn from soluble to insoluble forms by changing pH is fundamental for the fabrication of composite chitosan structure with specific functionalities. So, starting from this chemical behavior of chitosan, many methods of fabrication have been proposed in literature. The most representative are solvent evaporation, cross-linking, layer-by-layer assembly, electrodeposition, and also ionotropic gelation. In particular, the most used methods for the fabrication of chitosan membranes for fuel cell are the solution cast method and the layer-by-layer assembly. Here, we are focused on the ionotropic gelation method. Ionotropic gelation is a process based on the ability of some polyelectrolytes, so also chitosan, to cross-link in presence of contour ions, forming hydrogels. The advantages of this method are the simplicity and low cost, which are the most important and are related to the absence of sophisticated equipments. The use of aqueous solvents, the short times necessary to the process, and the reversibility of the physical cross-linking. Also, the possibility to have functionalized membranes directly in a single step. This is possible if we use a cross linker able to give proton conductivity to the membrane. What about drawbacks? Many years ago, the main disadvantage of ionotropic gelations was the low mechanical stability. However, today many solutions have been proposed. The most effective is the formation of polyelectrolyte complexes between chitosan and other polymers, for example, alginate, which is another biopolymer. So I will like to focus your attention on the fact that ionotropic gelation of chitosan has been used mainly in literature for the preparation of gel beds for biomedical application. Ionotropic gelation has never been used to fabricate chitosan-based membranes for fuel cells. So, in our last works, we have proposed this method, ionotropic gelation, as a novel synthetic method, named BIG in the following slides, to prepare green chitosan phosphotungstic acid membranes for hydrogen-oxygen fuel cell. So now I show you some of the more representative experimental results we have obtained. First of all, we have to answer to this question while combining chitosan and phosphotungstic acid. It is known that phosphotungstic acid has a very high proton conductivity, in the order of 10 to the -1 Siemens per centimeter at 25 degrees centigrade, together with non-corrosive environmental friendly features. However, it has a very low mechanical resistance and a high solubility in the water produced at the cathode of the fuel cell by oxygen reduction reaction. And this strongly limit the durability of the fuel cell power output. So to overcome this issue, in general, literature has tried to put phosphotungstic acid into a stable matrix. Among the different approach, we have noted that the capability of phosphotungstic acid to form insoluble complex with chitosan through the strong electrostatic interaction. This insoluble properties has been proposed by Cui et al. In about 15 years ago. And in that paper, the membranes were formed by two-step solution cast technique and the second step of functionalization. However, a few papers have developed this promising strategy with novel approaches. So we have proved for the first time the possible application of ionotropic gelation of chitosan to the synthesis of chitosan membranes with phosphotungstic acid. Here, in this slide, I show you the experimental procedure followed to synthesize flat proton conducting structure by ionotropic gelation. So, look at the first step 1. We use anodic alumina membranes as porous support. This support was immersed in high concentrated phosphotungstic acid in a solution in order to embed the porous structure. Afterward, step 3, the alumina phosphotungstic acid solution is dipped in the chitosan solution, step 3, by exposing only one phase, as shown in step 4. During this step, chitosan cationic polyelectrolyte and the phosphotungstate anions give place to ionotropic gelation, forming proton-conducting, self-standing membrane at the alumina sides exposed to the solution. Step 5. This film can be peeled off by the alumina support, and finally, the obtained self-standing samples were located in between those two cylinders in order to avoid wrinkling phenomenon during the drying process. After the big process, the membranes were also chemically treated by immersion in phosphotungstate solution for different times in order to study the cross-linking rate of chitosan. The ionotropic gelation through the big method offer the advantage to easily have chitosan synthesis and proton conductive sites generation in one single step, because, as said before, the chitosan cross-linker is also the proton conductivity donor to chitosan. So, phosphotungstate anions are injected across the polymer back face at the same time of chitosan gelation, permitting continuity in the through plane proton transport. So, on the contrary, solution cast preformed chitosan is not able to retain a good conductivity because of the limited surface to bulk diffusion of functional molecules through the polymer matrix. Also, instead of tedious cross-linking emulsion procedures, ionotropic gelation to prepare chitosan is a very simple and mild process. Here, I have simplified the ionotropic gelation reaction. You can see that negatively charged phosphotungstate polyoxo anions are amenable to ionical crosslink, the positively charged amine groups of chitosan. This occurs at the interface alumina chitosan solution. So a flat three-dimensional lattice of gel adherent to the alumina substrate is formed. The formation of ionic bond is supported also by hydrogen bonds between the H group of chitosan. And so it is possible to create a reticular network of immobilized polymer, which can be peeled off from the alumina support. So we have tried to monitor the big ionotropic gelation with time by measuring the same thickness by SEM of the prepared membranes formed at different gelation times and at fixed chitosan concentration. Basically, three main steps are involved, as you can see here in the sketch. In the first step, named 1 in the figure, we are in the first seconds of alumina immersion in the chitosan solution, and so anions of the acid and chitosan amines group came in contact at the interface and immediately reacts as expected for electrostatic ionic bonds formation. This is translated into a high initial gelation front rate, after which phosphotungstate anion diffuse into the initially formed polymeric gel and reach the chitosan solution, forming a new three-dimensional lattice of chitosan. Second step, the gelation front rate drastically decreased at 0.2, indicated that a new process controls the gelation kinetic. Finally, at about 20 minutes of ionotropic gelation, the gelation front rate became insignificant. So the membrane does not grow up. So in order to evidence the kinetically controlling phenomenon, we analyzed the different processes involved in the ionotropic gelation of chitosan. The electrostatic chemical reaction, it is expected to be very quick and does not controlling. The second process is the transport of phosphotungstate anion from the bulk of the phosphotungstate AC solution toward the alumina, toward the film interface, and also this is a process very quick and does not controlling. Finally, we have the transport of phosphotungstate anions inside the already gelled film. So we can hypothesize that the gel formation rate is mainly controlled by the diffusion rate of the phosphotungstate anion through the already gelled chitosan layer. This is confirmed by the experiments carried out at constant concentration of acid and variable concentration of chitosan. We have calculated the stoichiometric quantity of acid necessary to cross-link all the amine group of chitosan, and the concentration is 0.034 mol per liter, a value strongly lower than the one we have used in this experiment, which is 0.76 molar. So this indicates that chitosan is the limiting reagent of the ionotropic gelation reaction. Also, we can see that the thickness of the final film increases with increasing the concentration of chitosan solution. Also, by decreasing the concentration of acid, the mechanical properties of the final gel were not enough to self-sustain the membrane. So these results show that not all the acid anions are prone to cross-link chitosan, and also that cross-linking is essential to stabilize the structure, the mechanical stability of the polymer. So in order to investigate the effect of cross-linking, we have also made subsequent immersion of the membranes in a highly concentrated acid solution. The results we have discussed agree with EDX results, where we have estimated the tungsten carbon ratio. You can see that the tungsten carbon atomic ratio moderately increased in the first minutes of chitosan gelation, and after 30 minutes remained quite constant. So this is in good agreement with the slow diffusion of acid in the already formed film. It is likely that the cross-linking reaction needs low gelation rates to be more incisive. Also, we can see that in the post-cross-linking, the ratio increases, strongly increases, going from as formed to 60 hours of post-cross-linking treatment, and afterward it remains quite constant. So we have that 60 hours of post-immersion is the time necessary to have complete cross-linking of chitosan. I am probably over the time, so I go fast. I would like to show you the results obtained at our hydrogen-oxygen single fuel cell. You can see here the polarization curve and power output relating to different times of gelation. And you can see that the best performance is delivered from 30 seconds of gelation time for 2% weight volume of chitosan concentration. So these are the conditions identified as the best condition of synthesis. Here I show you the effect of the post-cross-linking time, and you can see that the polarization curve and power output are related to two different chitosan concentration and different post-cross-linking times. It can be seen that the power peak increases as the cross-linking time grows up to 60 hours, and afterwards slightly decreases. This data agree with EDX data showing that a time of 60 hours is required to complete the cross-linking process. As shown in all the recorded polarization curves, kinetic is mainly governed by the ohmic over potential, mainly attributed to the membrane proton conductivity. We have also estimated the membrane proton conductivity by in situ electrochemical impedance spectroscopy performed in situ in the single fuel cell fed with hydrogen oxygen at 25 degrees centigrade and at open circuit potential condition. It can be observed that the values of proton conductivity are consistent with those obtained by analyzing the fuel cell polarization curves in the pseudo-linear part of the curve. You can see from the figure that the proton conductivity increases as the post-cross-linking treatment time increased to 60 hours and then slightly decreased at 120 hours, confirming the previous results. The last slides, I show you some preliminary results about stability. We are studying we are continuing to study this aspect. This aspect is really crucial, obviously, for application of these membranes. From these preliminary results, you can see, you can see that the power output under a constant voltage of 0.45 show that after a decreasing during the first 10-20 minutes, the power density reaches a constant value for a few hours. From the figure, it can be also observed a good dynamic stability of the cell, which is able to restart after 12 hours off. So we are at the conclusion. What we can say that ionotropic gelation was successfully employed to prepare high proton conductivity chitosan phosphotanksic acid membranes. The experimental conditions for the synthesis have been optimized to reach high peak power density in a hydrogen-oxygen fuel cell, about 500 milliwatt per square centimeter. The time of 60 hours is identified as the time required to complete functionalization of the chitosan amine groups. And this suggests also that the ionotropic gelation step needs to be improved in order to have really a one-step procedure. Further insight into stability of the membranes under fuel cell operation is necessary, of course, for commercialization. So I thank you for your kind attention, and if you like to cooperate or make some question, I am available.
Thank you so much, ma'am. And it was indeed a very informative session, as mentioned by many of the participants. Though there is a small question from Dr. P.K. Singh, and he wants to ask why we use a specific concentration of PTA in chitosan.
Sorry, I have not listened to you. Can you repeat the question?
Yeah, so Professor P.K. Singh has a small question to make, and it is why we need to use a specific concentration of PTA in chitosan.
PP?
PTA, why we need to use a specific concentration of PTA?
Of phosphotanksic acid, you mean?
Yes, yes.
Okay, sorry. So why we need to use a high concentration of phosphotanksic acid?
Yeah.
Because we have seen that a lower concentration is not able to give the right cross-linking grade to the membrane, and so by using lower concentration we obtain membranes with a low mechanical stability. This means that not all the phosphotungstate present in the solution are prone to cross-link the amine in chitosan.
Okay.
So it is likely that we need the next step is that we need a process that is able to go not so fast in order to favor the cross-linking grade of the chitosan membrane.
Okay, ma'am. Thank you so much. And it was really an informative session. And
You are welcome.
Yeah, and I do not see any more questions here in the chat box. So if anyone has any question, they can ask directly. They can unmute themselves and ask. Or else, as we can see, Professor Patrigia's email ID is already mentioned here. So you can take a note of it, and if you have any more doubts, you can maybe directly reach out to her. So thank you so much, ma'am, for sparing your time and giving this very detailed presentation.
I remove my
Yeah, you can stop
Okay.
sharing the screen from your side now. And now I would like to introduce our next speaker of the session, Dr. A. Shukla, who is an associate professor at the Rajiv Gandhi Institute of Petroleum Technology, Amethi, in India. And he'll be delivering a talk on the thermal energy storage materials and thermal regulation of photovoltaic panels. And before I introduce Dr. A. Shukla to start his presentation, I would like to give a brief introduction about Dr. A. Shukla. Dr. A. Shukla has completed his BSc and MSc from University of Lucknow, and then he completed his PhD from IIT Kharagpur in January 2005. He worked in different institutes of uh, international repute, including IUT Bhubaneswar, University of North Carolina, Chapel Hill, USA, University of Rome, Italy, and Physical Research Laboratory, PRL, Ahmedabad. He is, as I already told, he is working currently as associate professor in physics at RGIPT, Amethi, and he is also head of division of basic science and humanities and chief vigilance officer in the RGIPT. His research interests include theoretical physics, nuclear physics, physics of renewable energy resources, including thermal energy storage materials. He has written 5 international books, and he also have many active international research collaboration and projects, which spans from University of Taiwan, Virginia Tech University, and other various other collaboration and projects he has by his side. So, with this brief introduction, I would like to invite Dr. A. Shukla to start his presentation. And sir, the floor is open to you now.
Okay. Thank you. Am I audible?
Yes, sir, you are audible.
Okay, just a minute, let me share the screen. Is slide
Yes,
visible
yeah,
now?
yes,
Can
sir.
you see
Slide.
that?
Yes, sir. Slide is visible.
Okay, thank you so much for the introduction. And first of all, I'd like to thank Dr. Meena Gupta and all the organizers to give me this opportunity to speak on thermal energy storage materials and thermal regulation of PV panels in this quality engineering and technological advances in material and devices workshop. That is one big online workshop come faculty development program. As you introduced, I'm working at Rajiv Gandhi Institute of Petroleum Technology, JAS Amethi. It's our institute comes under Ministry of Petroleum and Natural Gas, and our main mandate is to work related to the energy materials. Of course, mainly hydrocarbon, but many things other than hydrocarbon. Which are other energy related materials. So we are working in different research groups. So today I will be talking mainly about the thermal energy storage materials and also one of its application, which is basically the thermal regulation of PV panels, photovoltaic panels. So before that I come to the topic really, let me start my presentation from the buzzword of the climate change, which is like very common these days in different research spheres, especially because of the global warming. So long back in 1896, it was a Swedish chemist, basically Arrhenius. He is a very well-known chemist who concluded that this industrial age coal burning will enhance natural greenhouse effect. Now, those days, of course, still it is. It's a cold country. So his prediction was that this heating, the global warming coming out of this greenhouse effect will basically give a, of course, it will give a climate change, but it will be on the positive side. It will be basically make their colder climate turn into a little more warmer. So it will be kind of beneficial. However, he could not see it in such a way that this overall global warming could be actually harmful net effect for the mankind. Today, this climate change and carbon emission has actually given us different targets to reduce the uses of fossil fuels and move towards the renewable energy resources. And one of major renewable energy sources is the use of solar energy. So we can use solar energy basically two ways. One is basically the using PV panels. So we actively we can use we can get electricity utilizing photovoltaic panels. Another is the we can get we can store the solar energy in form of the thermal energy in different mediums, and this thermal energy can be used in different forms for different domestic as well as industrial applications, such as the water heating, building applications, and for very many different applications this can be utilized. So today I will be sticking mainly to thermal energy storage materials and its application basically for the thermal regulation of photovoltaic panels. It basically reduces the overall objective is to reduce the energy load on the for fossil fuels. There are mainly three types of thermal energy storage materials. One is one which are based on the sensible heat, such as like molten salt, sand, concrete, where the energy stored is in the vibrational mode of molecules. Second is the latent heat based thermal energy storage materials, where energy is stored in medium when it changes the phase, basically ice, water, wax, and different such materials. Such type of thermal energy storage materials are latent heat based thermal energy storage materials. And the next is the thermochemical energy materials. Such materials are basically consisting of those materials where energy is stored in chemical bonds of molecules, and through it is utilized through different chemical reactions. Metal oxides or reversible oxidation, etc., are the common example of such kind of energy storage materials. So the important parameter in any of these thermal energy storage material is the energy density, heat change into the density, or in other words, in very common language, we can say how much material is required to store particular energy required. So it is, and this kind of technology has been available to us for long ages. So, but the problem is that the larger volume of material is required to store the same amount of energy, especially in sensible heat storage. The other options are the latent heat and thermochemical energy storage materials are quite being investigated these days, and the work I am discussing today is based on the latent heat based thermal energy storage materials. So these thermal energy storage materials basically allow to the storage of heat or cold to be used later. Whenever the heat is available, one can store it and it can be utilized later on. This kind of work as the heat bank, basically, you can say. So to be able, now the material should be in such a way that you should be able to retrieve the most of heat stored after some time. So the method of storage needs to be reversible. It can undergo a thermal cycle without having any change in the medium or material. Thermal energy storage can be implemented by storage of sensible heat or latent heat, but basically we will be talking about the latent heat, which works on the phase change principle of the phase change. The most common way of thermal energy storage is as sensible heat, as I was just telling. This heat transfers to the storage medium, leads to a temperature increase of the storage medium. You think of any material, you provide energy to it, it doesn't change the phase, but it stores heat up to a certain extent. As you can see in the lower part of the diagram, here it's just changing the temperature of it, but it is not changing the phase. But once it starts changing the phase, then the heat stored is basically the latent heat stored. So hot water storage for domestic heating and domestic hot water is a very common example for the sensible heat storage. Now the phase change solid liquid in melting and solidification can store large amount of heat in comparison to the sensible heat storage mediums. So upon melting, while heat is being transferred to the storage material, the material still keeps its temperature constant. A very common example, you can think of a wax. When it stores heat, it just basically changes its phase. into liquid, and it changes the, and once again you take the energy stored out of it, it again goes back to its main phase, which it was solid phase. So if the melting is completed, further transfer of heat results again in sensible heat storage. As you can see, the third part of the diagram here in this picture, first is the lower part, the heat storage is in the sensible heat form. Then it is then the second part, you can see the latent. So when the phase is changing, the storage is in form of the latent heat. Then again, if you still heat it up or provide the thermal energy, the phase change has completed. So further the energy will be stored in the form of the sensible heat, and this process is reversible, so that the energy is released when it changes the phase again. So the heat supplied upon melting is called as latent heat, and the process is called as a latent heat storage. The materials which are commonly used for the latent heat energy storage are the phase change materials. So basically, a phase change material is a substance with a high heat of fusion, which upon melting and solidifying at a certain temperature is capable of storing and releasing large amount of energy. The main criteria to select a PCM for any given application is that it should be able to store or release large amount of energy in the smaller volume. As you can see, the PCM in this figure, PCM in solid state, once it temperature rises, the PCM melts inside it and it absorbs the heat energy. Here, the red part of it, and again temperature falls, it again gets it releases the energy. So here in the right part of here, you see the temperature it is storing, and the left part here it is the increasing, it is releasing the thermal energy. So it is again being solidified, and it again goes back to the PCM in the solid state. So it is a cyclic process basically. So the same material is being utilized again and again without any change in the property of the material. That is one another important property of such materials, so that these materials should be stable with respect to the thermal cycles. These should have the capability of storing heat and can be utilized for heating cooling at almost consistent temperature. This should be easy to use, long life, and easily rechargeable thermally. So as I was telling you, that the principle of these phase change materials or latent heat energy storage materials is known to us since long, but the problem is to devise proper material and the proper application based on it with respect to the temperature of the application. So the choice of PCM basically depends mainly on two important factors: the latent heat of phase change and the phase change temperature range. So suppose you want to apply the phase change material for the thermal regulation of photovoltaic panels, you may have to use different phase change material. If you want to use phase change material for the indoor comfort of the building, you want to apply in the building, then you need to go for the different phase change material. Similarly, you may have seen commonly a PCM kept in the freezer of your refrigerator, that is also a phase change material. So depending on the different application to application, one requires to design new phase change materials which are more efficient, energy density is high, which are
I guess there is some network issue. Hopefully, Dr. Shukla will be back with us just in a few seconds. So, everybody, please be patient.
Tina, I am calling him.
While we are trying to solve the network issue, I request you all to not leave the meeting and just wait for a few seconds so that Dr. Ishukla can resume his presentation.
Hello, Dr. Tina. Sir has joined, so I think you just call him.
Yes. Dr. Shukla, can you hear me? Dr. Shukla? Dr. Shukla, are you able to hear me? Yes, sir has joined. I think maybe he's just trying to share his screen again. Uh, Dr. Shukla, can you hear me? Dr. Meenal, can you check the status with Dr. Shukla? He is in the
Actually, I am
meeting.
calling him, but he is not receiving the phone call. So that's why I am also waiting for him.
Yeah, so he has joined us back in the meeting. Let's hope the issue will be resolved soon.
Yeah.
கல்யாணம் இருக்கு அப்படின்னா நீங்க இந்த மாதிரி ஒரு மொத்த கூட அவளை கூட உங்க போட்டோம் எக்ஸ்ட்ரா வந்துருமே நம்ம ரிட்டர்ன் கிஃப்ட் கொடுத்த மாதிரி ஆயிடுச்சு. அதே மாதிரி பாத்தீங்கன்னா நல்ல சாரி நம்மளுக்கு கிடைக்கும். நீங்க பாருங்க இதெல்லாம் பாத்தீங்கன்னா 1050 ரூபாய் உங்களுக்கு ஒரு சாரியோட வேல்யூ. இந்த ஒரு சாரி
Dr. C. Ramesh Kumar, can you please mute yourself?
இதோட ஒரு காட்டன் சாரி இதோட வேல்யூ பாருங்க. இப்போ மெயின் சாரியா நம்ம இந்த இடத்துல பாத்தீங்கன்னா சக்கரம் டிசைன்ஸ்ல
Okay, so dear all participants, I am calling him, but he is not able to attend my call also. So let's wait for few more minutes and then we will decide what to do once I contact him.
We are really sorry that we have to wait and we are facing this network issue here. We are trying to resolve it as soon as possible. So just be with us for some time and hopefully the issue will be resolved. So